nanohub.org.
All right, so we're in the last lap, and we're going to be doing some special topics this week. We have been doing special topics last week as well. Professor Reifenberger talked about electrostatic force microscopy in a lot of detail, Kelvin force microscopy, and so hopefully you're up to date with those methods. The task today is a pretty challenging task. To try and cover atomic force microscopy in liquids in one or two classes is very difficult. But it is, after all, given the scope of the whole class, it can only be treated as a special topic, which means we can't cover too much in this area. All right. So of course, the first question is, we've been doing atomic force microscopy in air and in vacuum. We've talked about it. Why would you want to go into liquids? Of course, the main interest in liquids is to do biology in liquids, because the structure of most biological samples is very significantly affected by whether or not they are in what's called a native state or not. So a protein or even DNA in native state would be its natural geometric conformation while it is in a liquid solution, as it is in the human body, or whatever biological entity we're talking about. And in biology, structure often follows function, or decides function. So what happens is, if the very structure of what you're looking at is modified by the presence of the saline water-based solution that all of biology happens in, then of course the function is also affected by it, right? So the whole idea is, can we use atomic force microscopy in liquids to try and study biological samples in what is called native state, i.e. as they would be under normal biological conditions. The reason why this emphasis is important is because before atomic force microscopy, the other methods for looking at biological samples, imaging and studying them, typically involved electron microscopy or X-ray crystallography. Those are two techniques that are, of course, extremely high resolution, but from this point of view, both of them suffer in the sense that you cannot observe the structure in native state. Because both for electron microscopy, X-ray crystallography, you're looking, of course, at not doing this under liquids. In fact, often under vacuum conditions, and often under cryogenic conditions where the atoms are not moving anymore and are kind of fixed at low temperatures. The other thing that happens with X-ray crystallography is, if you think about X-ray crystallography, it is in effect an averaging technique. So you take, let's say you're looking at the structure of a virus, you would crystallize that virus, or if you're looking at structure of a protein using X-ray crystallography, you produce crystals of those proteins, and then you study the structure by looking at, the X-ray sort of scattering of what you see, and you use Fourier transforms to back out, where the positions of the different atoms are going to be. Of course, when you do a Fourier transform of the image and try to back things out, reconstruct using X-ray crystallography, it is in some sense an average. So you're assuming perfect crystal periodic structures, then it works out. But in many cases in biology, if you don't have perfect periodicity, then effectively what you're doing with X-ray crystallography is some sort of an averaging over multiple samples. The same thing actually happens with when you do electron microscopy of very small structures. There's some amount of averaging involved. So if you want to study a single entity, let's say a cell or a virus or DNA or protein, in native settings, perhaps atomic force microscopy is the best way to do it. Okay. The knock against atomic force microscopy is that it's not truly native state, because after all, to do atomic force microscopy, you have to somehow immobilize your sample on a substrate. And that is a problem, because it's not mimicking a natural setting. So this is one of the key points about it. So that's why people start referring to the advantage of AFM as being a method by which you can image biological samples in quasi-native state. So it's not really native state because you're somehow immobilizing the structure, and that's not typical or representative of what happens, for example, in the human body. The other knock against atomic force microscopy in its claim to be true native state physiological conditions is there's a lot of debate about what really is meant by physiological conditions. Is it okay to do imaging of a cell in a clean buffer solution like PBS, or does real physiological environment mean putting it in a buffer solution very similar to what it would encounter in the human body, which is much more complicated than what it would be in a simple PBS saline buffer, for example. So those are all questions and debates, and therefore, at the end of the day, I think we are safe enough if as AFM people, we simply claim it's quasi-native or quasi-physiological condition imaging. Okay? And we're able to study single particles or single structures without having the need to average over the geometry of multiple replicates of the same structure. Okay, so these are all examples of AFM images, arguably some of the highest resolution images for biological objects, has come out of the group of Daniel Miller, for example. Surprisingly, or rather not surprisingly, they use contact mode very often for these things, really soft cantilevers. And so, for example, this is an AFM image of a whole array of protein motors that have been immobilized on the substrate. Now, biology is, of course, the defining reason for trying to do atomic force microscopy in liquids, but of late, there's been an interest in studying, without biology, what happens at liquid-solid interfaces. There's a lot of interest in that, too. The reason for this interest comes from a variety of problems. So when you're dealing with, for example, environmental science, there's a lot of reason to understand what happens at the interface of water with solid objects, what happens to adhesion, what happens to, chemical interactions at these interfaces. So there are a lot of people just studying water-solid interfaces themselves. And the atomic force microscopy helps you really measure interaction forces at those interfaces. So that's another reason to put AFM into liquids. If, for example, you want to study adhesion in liquids, if you want to study electrostatic forces in liquids, if you want to study what are called solvation shells in liquids, all these things, you just go to liquids, even if you don't do biology, right? So there are a lot of reasons to be doing things in liquids. I do want to, right from the get-go, point out that when you do things in liquids, especially when you do biology, probably more than 90% of the effort goes into preparing the sample. Professor McNally is here. She's an expert on doing this in live cells, and I'm sure she'll also attest to the fact that sample prep is 90% plus, if not 99% of the effort involved in this, okay? And this is a very tricky issue, and depending on what you want to immobilize, whether it's DNA or protein or bacteria or living cells, there's a whole lot of surface biochemistry that you need to understand. And the physical principles behind what you choose to stick things on a surface is a pretty complicated thing, all right? I will point out that there are many specialized techniques. So if you follow the literature and look at the materials and methods section of every paper published, they will describe in detail the method they use to immobilize whatever biological sample they are studying. So I encourage you to follow some of those recipes carefully and apply it to your own sample. There are also web pages, for example, and application notes. Vico, for example, has one. I believe Asylum also has one, and Agilent, where they provide examples and protocols of sample prep for different kinds of biological samples. So I encourage you to look at those also to get an idea. The key point, the reason I'm telling you this is we're not going to be discussing this in this lecture because, again, it's a very complicated issue. It itself will take a whole, at least a whole lecture to put together, because what I want to emphasize is that the physical mechanism, so if you look at the ways of sort of binding a biological sample to a substrate, there are, just for DNA, for example, depending on the kind of DNA you're choosing, there could be half a dozen or a dozen different ways of doing this. And the physics behind each one is different, and the advantages, disadvantages are very different. The chemistry is different. So, to really try, and the substrate, whether you want to do it in glass versus you want to do it in mica versus you want to do it in graphite, very different things, very different objects, right? To understand what method you choose to immobilize a sample. So, there's not a very clear unifying theme where one or two or three basic mechanisms can be used to do everything. At the moment, the area seems to be more of a list of recipes, that you follow, and they work, some don't, right? So that's why it's hard to put everything together under common physical principles for immobilizing biological samples. So with that in mind, just to give you a brief overview of what are some of the things that happen when you take an AFM cantilever and put it into liquids to try and image biological samples. This is a chart I put together based on Michel Dom's book and also Jonathan Howard's book. Give you an idea of, what are the length scales on the left column of what we're trying to image in biology. The AFM tip radius is roughly, as just mentioned, of the order of 5 to 10 nanometers in radius. We're trying to image sometimes viruses that can be anywhere up to, tens of nanometer to 100 nanometers in size. You can go up to whole cells, and depending on the cells you're looking at, you could get cells roughly that could be 50 microns in diameter or an extent. It could be as large as that, where the heights could be 1 or 2 microns also for cells. So we're really looking at a very large range. At some point, you're also interested in perhaps imaging DNA or proteins, for example, and you're looking with DNA at looking at an object whose diameter is of the order of a nanometer, right? So you're really looking at using objects or imaging objects that change in size from, let's say, critical dimension of less than a nanometer to all the way to microns if you're doing living cells. All along, of course, your tip radius is about 5 nanometers. So you can imagine that whenever you're trying to image things like DNA or proteins, you have to worry about tip convolution very much, right? The fact that the tip is larger than the critical dimension of the object you're imaging means that the width of what you see is not the real width, and the convolution of the tip makes a big difference to your image. You've had a chance to talk about tip convolution in one of the Veda classes, so do refer to that class. Whereas when you're dealing with larger objects, typically bigger viruses or living cells, for example, or bacteria, you don't worry too much about geometric tip convolution effects. It's important to look at forces in water. One of the key things that happens is as you just try to oscillate a cantilever in water, there's a lot of hydrodynamic forces on the cantilever. In water, they actually end up being of the order of hundreds of nanonewtons themselves. So, for example, if you wanted to do an FZ curve and you move very fast, let's say typical speeds towards the sample, just the motion of the cantilever to the sample makes the cantilever bend up before it contacts the sample. So in other words, your bending signal would then also be measuring hydrodynamic drag forces. This does become an issue because when you do FZ curves pretty fast in water, one of the issues that happens is it's not this clean straight line and then you hit the sample and something happens. You actually get hydrodynamic drag effects that when you approach the sample, even before you contact, there is bending quite a lot. And then you contact and there's some force, and when you come back, it bends the other way, because when you come back, it's bending down. When you go down, it's bending because of hydrodynamics. And so that causes a very major distortion of a standard FZ curve. I think we mentioned this when we did artifacts. We had a lecture on artifacts and FZ curves. We talked about this. But it's a big effect in liquids, the hydrodynamic drag. And it's often, as I said, of the order of hundreds of nanonewtons, depending on the speed at which you approach. There's a very important question in biology is when you tap, let's say, or when you image, what forces are you applying on the sample? How big should they be? That example problem in the homework asks you to, on a polymer, figure out conditions under which you apply less than 5 nanonewtons of force. The question is 5 nanonewtons too much for biology or too little for biology? And, the answer is it depends. If you're looking, for example, at viruses, if you're trying to study individual viruses, when you apply about a nanonewton of force to a virus, it typically buckles and collapses. So the shape and the height that you're observing are not going to be right. So, which means that certainly when you try to do things like viruses, you are trying to apply forces that are just a couple of hundred piconewtons, or 0.2 nanonewtons. 1 nanonewton or 2 would be too large for them. On the other hand, if you're looking at protein crystals, like Bacteriorhodopsin, for example, is a membrane, but it consists of tightly packed protein clusters. And for that kind of a sample, going up to 5 nanonewtons is not such a big problem. You can still get reasonably the decent height out of it because it's a pretty stiff sample. All right. So you do need to worry about the forces depending on what you're dealing with. But again, in liquids, be clear that regardless, you simply don't have the leeway to apply forces like 10 nanonewtons. That just is not okay. You need to keep your forces 5 nanonewtons, I would say, is really on the upper limit when you do biology. For really stiff biological samples, for the most part, you should be applying about a nanonewton or less. Which, of course, requires you to use soft cantilevers typically. So, for example, in air, most cantilevers you're using are, for tapping mode, let's say 20 to 40 Newton per meter. If you want to do force modulation in air, you might be using 1 to 10 or 5 to 10 Newton per meter. But in liquids, you typically have to use cantilevers that are less than 1 Newton per meter. You have to use cantilevers that are 0.5, 0.05 Newton per meter kind of cantilevers. So you apply gentler forces. Okay. Another important scale here is time scale. Just to give you an idea of what are some of the important time scales you might be interested in observing in biology, because it's a good question to ask. When you're taking an image, can you actually observe at the speed at which you image? Can you observe dynamic processes in biology, right? And just to give you an idea, when you're looking at things like conformational changes of proteins, for example, they typically happen at length scales that are fast, or time scales that are much faster than your oscillation time scale of the cantilever. So it's usually hard to observe conformational changes. It'll be nice to take subsequent images and seeing a protein standing like this, and then you change something and you see it gradually morphing and changing, and those kind of things are hard to do with normal AFM unless you have a special way to slow down that process. But conformational changes are much faster than AFM timescales typically. All right, so you're typically able to observe relatively slow processes as they occur. Okay. All right, so we'll talk a little bit about what are the interaction forces of relevance when you go to liquids. Probably the most important one is electrostatic and van der Waals forces in liquids. Okay. Now, the key theory that helps explain this is the DLVO theory. We talked about this when we did interaction forces. There was some discussion about DLVO forces, I believe, and I've probably done in more detail then. But roughly what happens is when you have two solids in an ionic medium like water, two kinds of processes occur. So your material itself could be, or solid could be a semiconductor, or could be a metal, or it could be an insulator. In any case, either you have some trapped charges on the surface, or you have a contact potential or a surface potential, whatever it is you're dealing with, right? So what ends up happening is either because of the surface potential or charge on the surface, you have a polar medium. And so what ends up happening is there's an effect called screening of charges that automatically happens in liquids. So you have a positive charged surface, let's say. Water is a polar molecule, so it has a dipole associated with it. And so what ends up happening is this positive charge attracts, the negative part of the water molecules to it. And so what ends up happening is, quickly, any positive charged surface gets covered with water molecules with the polarity in a way so as to neutralize the effect of the positive charge, so that a certain distance away from this positive charge on the surface, you won't feel the electrostatic force because it's been counterbalanced in some sense by this cloud of polar molecules, water molecules that have, gathered around the positive charge. This effect is even more strong when you put in some ions into water, when you have an ionic solution of water, because now you have free ions, sodium ions, potassium ions, that will do that for you. You have a negatively charged surface, the ions will simply migrate and actually start assembling, in a sense, shielding the positive charge that you have, right? So the point is, this effect I'm talking about happens in polar media, for example, with water. When you have ions, when you dissolve salt in water, it becomes very strong. Because now you have free positive, it's not just a dipole moment of water molecule you're using to shield, you're actually using full positive or negatively charged ions to shield your charges. Okay? So the key thing in water that happens, number one, is the electrostatic forces get shielded. You feel them only a certain distance away. And the extent of shielding depends on the polarity of the liquid, it depends on the salt concentration in the liquid, and so on. Okay? So, that's that. You also have van der Waals forces in liquids. It's not that they don't exist. They do exist in liquids also. So, the DLVO interactions, for example, as stated here, would suggest that the interaction forces between a spherical tip and a flat surface are given by the following formula. The latter part of this is the attractive van der Waals force that we have talked about before. This part, the first term, depends on d, the gap between the sphere, i.e. the tip, and the surface, has an interaction force dependence that's exponential, e to the minus d over lambda. Okay? So what that means is, this part of the interaction force acts over a length scale of lambda, right? Because beyond lambda, beyond d equal to lambda, this dies out. This first term is very small, right? When d becomes greater than lambda, it's very small. So this lambda is called the Debye length in liquids, okay? Now, lambda depends on multiple things. Typically, it involves temperature, but it also has the concentration embedded in the denominator. So as you increase the concentration, ionic concentration, you actually decrease the Debye length, right? So as C goes up, lambda starts coming down, and lambda effectively is the length scale over which you feel electrostatic interactions, okay? So you have a way to control this length scale by controlling the ionic concentration of the solvent. The other thing you have is you can control also what lies in front here, sigma T, sigma S. Sigma T, sigma S are connected with the charge density on the tip, charge density on the surface. And so you can also sort of influence these electrostatic forces by using different materials for the tip and the sample, or coating them with molecules that have different charge densities. So you have two ways in liquids of influencing electrostatic forces. One is by changing the surface charge densities of the interacting surfaces, so you can coat your tip or sample with certain molecules. Or you can play around with the ionic concentration of the solvent, which adjusts the lambda, okay? So the two important things I want to point out here are, number one, if you look at the signs, you find for that the first term is going to be repulsive. Yes?
So, quick question. Is A in the second term there, is that the same as Helmholtz constant, or is it corresponding Helmholtz constant for samples, or?
Yeah, I mean, it's a Hamacher constant. The mechanism is exactly the same as what you have studied before. Okay. Again, if you go into the theory of exactly Hamacher constants in liquids, Israel Ekvali has a very good discussion of how to do this calculation in liquids and so on. All right. So at the end of the day, whether or not the first term is repulsive or attractive depends on sigma t, sigma s, correct? So if the charge density on the two surfaces are identical, both are negatively charged, then you start getting repulsive interactions, or sometimes you can actually get attractive electrostatic interactions also, okay? Although under most conditions, the electrostatic forces, if you think about them, are most likely going to be actually positive, i.e. repulsive, okay? All right. So let's see what this looks like. I can plot those graphs, those formulas for different values of ionic concentration, but I thought of presenting some experimental results to get you an idea of what these interaction forces are and how they depend on the parameters of interest, okay? On the very top, what you find is FZ curves made between a cantilever and a hard sample. I believe it is mica in this case. This is from Miller's review article. And what is done is you see a distinct sets of FZ curves, right, taken with different salt concentrations. Okay, so the cantilever is the same, the surface is the same. All you're doing is changing the salt concentration of the liquid, of the water. What you find is when you add 50 millimolar of the solution, well, let's start from the very top. You have 20 millimolar of potassium chloride in solution, right? So it's a relatively low concentration. And as you approach the sample, you start seeing a repulsive interaction, correct? So the cantilever starts bending up at a Z value of about 50 nanometers, correct? Right? So at a Z value of about 50 nanometers, at the very top, which is in parentheses labeled 1, the cantilever starts bending up, and you can argue that you finally might touch the sample at a Z value of about 25 nanometers is when you see that the red curve roughly joins what you would get if you had no interactions and just a direct contact with the surface in a 45-degree curve as expected on a hard surface, right? So what that would suggest is when you are using the 20 millimolar potassium chloride, that the length over which the interaction forces begin is roughly 25 nanometers. It's from 50 to 25, so the Z distance, or the gap at which interaction forces begin, is roughly 25 nanometers from the surface, right? And this is a repulsive force because the cantilever bends up, okay? So this would be an example of how you feel electrostatic forces, and what they do is they sort of make this interaction force gentle. You get a gentle repulsive slope until you hit and contact the sample. After you contact the sample, of course, you have a repulsive gradient. But having a low concentration, what it does is it makes the interaction over a slightly longer length scale. It's not a sudden no contact and then contact. There is this gentle repulsive force region that comes up as well. As you increase the salt concentration, you find that the Debye length, i.e. the length over which you feel the repulsive force, starts shrinking. And in this particular experiment, at the highest salt concentration, and of course, this depends on the valency of the ions there. Magnesium is not the same as potassium and so on. And so all this you have to take into account. The key point is when you choose a 50 millimolar magnesium chloride and potassium chloride, you actually effectively have screened the electrostatic forces completely. And the cantilever feels no force until it touches. And then repulsive force comes in. So if you as an AFM person are interested in measuring elastic modulus of a sample, you would probably try to use high concentration because you don't want, when you try to study properties, mechanical properties in liquids, you need to make sure that only certain kinds of interaction forces are available, not others, right? So it would be hard for you to try and do a Hertz contact if you had the top curve. Then you'd be fitting Hertz to what is really due to electrostatic forces. You see what I'm saying? So if you actually use the concentration shown on the very top, you'd get this gentle repulsive force, and if you then applied Hertz contact to try and fit that, you would get a very soft elastic modulus because you're applying a contact theory to a force curve that is due to electrostatics, right? So you get completely wrong answers. So if you want to get a good answer for elastic modulus, you want to screen away all other possible forces. You would do that by going to higher concentrations so that there are no interaction forces, and then you touch the sample and you indent it. And then, of course, you would have to convert FZ into FD, remember? And FD, you would fit to a Hertz contact model. It's not simply a question of ionic concentration. The pH of the solution plays a large role also in these interaction forces, the DLVO interaction forces. So this is something taken from your reader, the Bud Capella and Capel review article in the reader. And here again, you got force versus distance. In this case, this is versus D, not Z. It's actually D. They've converted it FZ into FD in this case. So this one is FD. And the pH is being changed of a particular solution. And you see how changing the pH makes you transition from a repulsive to even a possibly at high pH an attractive region also comes up in the interaction. So pH and salt concentration both influence the DLVO forces that I showed you on the previous page. Okay? So this is giving an idea of the kind of interaction forces and how you can control them in liquids. Again, so this is simply, again, a mathematical statement of those interaction forces, the same formula as I showed you. Let's talk a little bit about what other forces are possible in liquids. One very important force in liquids, again, we won't have too much time to talk about them, are solvation and hydration forces, okay? Let me tell you a little bit about solvation and hydration forces. They are sometimes used interchangeably, and some people argue that the term hydration forces is not the right term to use for these things, but you know, let's have a broad general discussion on what these forces are referring to. So, roughly speaking, what we're talking about here is the fact that, you know, you got a tip and you got a sample here. At the end of the day, when the tip comes and contacts the sample, there are interaction forces, of course, but there has to be an interaction force that has to do with the force required to clear the water out of the interface. There's water on the tip, there's water on the sample, there's water in between. At the end of the day, when you make contact, you've had to do some extra work to physically move the water out, right? That's what we're referring to here, right? This is not about the electrostatic forces, this is not Van der Waals forces, this is physically what you need to do to push the last few layers of water molecules out so you can make a contact, a solid-solid contact, okay? These forces are, I would argue, quite difficult to measure. They are difficult to model even. And there are two components to these forces. There is one called an exponential component. So basically, you know, as you come close, there are models that suggest that this hydration force would be like an exponential profile, that as you come closer, you need exponentially larger force until a certain point where you've removed all the water and you're in contact with the solid. Yet another group of people points out that this interaction force is not purely an exponential force, but actually has oscillatory sort of, you know, fluctuations superposed on an exponential backbone. That has to do with the fact that, you know, when you come when the tip sample gap is so small that there are just 2 or 3 or 4 layers of water that remain between. The water is not this free tumbling water anymore, right? That when you confine water in a gap of, let's say, 3 or 4 angstroms, you're going to get pretty much layered water. Water layers together very much like ice. It becomes semi-crystalline almost. You can think of it also from the point of view of if you have a crystalline substrate water molecules, that the first layer of water molecules that sits on a crystalline substrate is going to do so in a very ordered form, because you're sitting on a crystal, right? So there's a certain pattern of charge densities in a crystal and polarities in a crystal. So the water molecules are going to sit in a very crystalline fashion somehow. Our image of what water is like is that are roughly tumbling, polar molecules in the bulk. But the first layer of water is going to be this organized, single, like ice-like crystal on a surface. So at some point there has to be a transition between this representation of freely tumbling water molecules in the bulk and organized crystalline-like structure of water on a surface. The general thought is that this transition occurs over 3 or 4 layers of water. So first layer of water is very nicely stuck to the sample. After that, there's a slightly more mobile layer of water, again ordered, and then there's increasing disorder until at a certain distance, it's freely tumbling water. So now we're talking, and all this happens, of course, in the last 4 or 5 angstroms, 4 angstroms, let's say. And so the tip then has to move these water layers aside. So this other group that talks of interaction forces due to hydration forces says that not only do you have this exponential the backbone, you have these oscillating trends superposed on it that has to do with the fact that, as you push one layer of water aside, you'd apply a little force, and when you remove that water layer, it relaxes. And then you push again, you push another layer of water, you get a greater force, and then it relaxes as soon as you popped it out. So you're like sort of popping water layers aside, if you will. So, of course, people have done simulations to show this as well, but roughly speaking, you have solvation and hydration forces. Okay, that's what this refers to. It is extremely hard to model, and I would suggest that think of these things as probably the cutting edge of research today is trying to understand hydration and solvation forces. Solvation typically refers to the oscillatory component. Hydration refers to the exponential component. It doesn't matter. At the end of the day, all it refers to are trying to identify what forces does it need to clear out the water, the last few layers of water, and then make contact, right? So it literally is forces required to separate water, push water out, and then make contact, okay? So it's a big area of research, and there's a good description of it in Capella and Kappel's review article. Besides that, you have hydrophilic and hydrophobic interactions. That's different. This has to do fundamentally with chemical interactions, okay? So, for example, if you have a hydrophobic surface and a hydrophobic tip in liquids, what that means is the tip does not want to have water around it, and the surface doesn't want to have water around it, but you've immersed it in water. So what happens is, as you bring the tip close to the sample, the two solids prefer to be stuck to each other as opposed to being surrounded by water. And you get large adhesive forces, what appear like adhesive forces, that are not really van der Waals, but are simply due to these interactions. Hydrophobic, two hydrophobic surfaces in liquids will want to be together. Another interesting thing that happens in liquids is the possibility of nanobubbles. If you start with an extremely hydrophobic surface in water, again, the surface doesn't like to have water around, so it's trying to push water, and so bubbles are created often. This is an example of it, again, in Capella and Kappel's article in the reader, okay? So actually what has happened here is you get all these nanobubbles, and they've been imaging that particular section, and the imaging made the bubbles coalesce and produce a big bubble shown there. Okay, so these are some of the forces we need to worry about in liquids. Each one of these forces would take an entire lecture to go into details. Hydration and solvation forces would take possibly even a whole month to really understand in full detail. Okay, but I'm just making you aware. Okay, now let's talk a little bit about what happens to the cantilevers as you put them into liquids. I think I mentioned this before to you. One of the key things that happens is if you took a tuning curve, or let's say a thermal response in air, you would, of a typical cantilever, in this case this is a biolever from Olympus, you would get a curve as shown in black. You might have a resonance frequency in air of about 45 kilohertz. You put it in liquids, and again, if you look at the thermal peak, you will find that that frequency is shifted to, let's say, what's shown in blue, to about 8 kilohertz. So from 45 to 8 kilohertz, it's a big reduction in frequency, and it primarily has to do with the fact that you have a lot of added mass effect. So that as the cantilever is oscillating, it's not just moving its own mass, but it has to move along with it the mass of a large amount of fluid next to it. In fact, the hydrodynamic mass of the fluid it can be shown is roughly 10 to 20 times the mass of the cantilever itself. It's a very large added mass effect, which shifts the frequency to the left. The second thing that happens is the resonance curve, instead of being so sharp, becomes broader because there's also greater hydrodynamic dissipation. And so Q factor starts reducing in liquids. Okay? And of course, a third situation that I really want to point out is for soft cantilevers, it's very important to understand that when you do the tuning curve far from a surface, thermal tuning, look at the thermal curve, when you do the same curve, when you're within imaging distance of the sample, it'll look a little more like red. The peak shifts even further. So the difference is between air and liquid, but even in liquid, there's a big difference when you're withdrawn from a sample as opposed to when you're very close to the sample. So the distance from the sample makes a difference to this curve. I can't emphasize this enough, but for a lot of triangular cantilevers that are used, this becomes a very important issue because triangular cantilevers have very short tip lengths. They typically have tip lengths of 3 to 4 microns, as opposed to rectangular cantilevers tend to have longer tips. So when you have very short tips, one of the problems is this squeeze film effect due to the presence of this solid surface becomes very high, because if the tip is very small, that means the whole area of the cantilever is much closer to the sample. So you're squeezing the liquid quite a lot, right? Whereas if you have a long tip, like 20 microns long, you keep the bulk of the cantilever pretty separated from the sample. But if your tip is 3 microns long, your cantilever is really squeezing. It's got a sandwich of water. It's really squeezing that a lot. So you get a lot of added mass effect due to that effect. So I want to point out that when you, in your AFM systems, when you engage the sample and you withdraw and you do a tuning curve, let's say thermal tuning, that is not the true Q factor and natural frequency when you image. Because when you image, your cantilever is going to be, your tip is going to be more about a distance of a few nanometers from the sample. But when you hit withdraw, you've moved aside maybe 2 microns from the sample, right? So that difference of trying to do a thermal tune, being 2 microns from a surface or being very close to the sample surface makes a big difference to what you're observing. It's a very important effect to take into account. Unfortunately, it's not very easy in most AFM systems to withdraw just by 10 nanometers and do a thermal tune. It's not so easy. Right. It's all set up to do one click and you withdraw 2 microns, and so you really move far away from the sample. Okay. This is just giving an idea of, there's a lot of work in trying to understand exactly how this distance dependence comes in, how the fluid dynamics makes a difference to all these things. There's a list of references here that I can point out to you. Really don't need to go into more details here. Also want to point out that, there's a lot of work in trying to understand how sort of cantilevers oscillate in liquids, and the key result here is, we've talked about eigenmodes, right? We've talked about eigenmodes of cantilevers and stuff. It's a valid question to ask if the eigenmodes are the same in liquids as they are in air, because all our analysis was in air, right? Do the eigenmodes remain the same or not? It turns out that if you make direct measurements of the eigenmodes, let me bring your attention to the rightmost column here. What you've seen is the second eigenmode shape. And what you find is in water is in blue, in air is in red. And you find that if you take a cantilever without any tip on it, so most AFM cantilevers have a tip, right? But if, let's say you take a cantilever without a tip, you actually find that there's no difference in eigenmode shapes in air and water, even for the first mode, which is shown in the first column, or for the second mode. But when you go to the second mode, of a tipped cantilever, so a cantilever with an AFM tip on it, you actually find, as you see in the rightmost column at the bottom right, is the eigenmode shape of the second mode is very different in air versus water. What this means is that if you want to do a thermal calibration or a stiffness calibration of second mode, you better do it in water as opposed to in air. Like, it's a very valid question. When you do stiffness calibration, should you do it in air and then immerse the cantilever in water, or should you do stiffness calibration in water itself? So this suggests that, at least for the second mode, you need to do the stiffness calibration in water, because if you do it in air, the shape of the mode is completely different, so you'll get different answers out of it. So the suggestion is to try and do calibration in the medium in which you're imaging sample. Stiffness calibration. Okay? And the reasons for this whole effect are described in the paper that I showed you. Okay, now I want to get to talk to you about a very important thing that happens when you put a cantilever in water. And that has to do with acoustic versus direct magnetic excitation. Okay, so what you're doing when you're doing acoustic excitation or using a dither-piezo is effectively you're applying a piezo shaker somewhere behind the cantilever holder. So you've got some sort of a plastic face, and you've got a place to put your chip and clip the chip on, and the piezo is typically on the back side of it, shaking. So the piezo applies a alternating expanding motion like that, and that vibration is then transferred to the chip holder, to the chip, and from the chip to the cantilever. But ultimately what it causes is it moves the base of the cantilever up and down. So ultimately what you do is you're shaking the base of the cantilever up and down. And when that shaking frequency equals natural frequency, then you get large amplitude motions, right? When you do things like a magnetic excitation, which is you coat the cantilever with the magnetic material, apply a oscillating magnetic field, then you shake only the cantilever itself. You don't shake anything else. Okay? Do you understand the difference between these two parts? What I want to emphasize is what shakes and what doesn't shake. Okay? When you do dither-piezo excitation, not only does the cantilever shake, but everything from the piezo to the chip holder to the chip to the cantilever, everything shakes. Okay? Whereas when you do magnetic excitation, you're trying to shake only the cantilever alone. Nothing else is going to shake. Everything else remains solid. Okay? That's the big difference. So many AFM systems allow you to choose between magnetic excitation or what are called direct excitation mechanisms, or dither-piezo acoustic excitation. All right? One of the key differences that arises, besides the fact that you're shaking many things when you do dither-piezo, is the fact that when you shake many things, so for example, let's say the base of the cantilever is shaking, right? That whole base of the cantilever is shaking, the chip holder is shaking, the chip shaking is going to shake the liquid also around it, and that liquid shaking is then going to shake the cantilever. So one of the problems that arises with dither-piezo excitation is how you shake the cantilever. There are two mechanisms. One is you shake the base and it moves, but as you shake the base, you're also shaking the entire chip holder assembly, the piezo, and that's moving the water around, and that water ends up moving the cantilever as well. So it's there's a fluid-borne path and there's a structure-borne path to the shaking that happens, okay? And I want to just end with this discussion. But so here's an example of what would happen if you do a tuning curve. So you sweep the frequency and look for a resonance peak in liquids. If you do magnetic excitation, you would get a response shown on the top right in green. The green is a magnetic response, so you would get a very clean resonance peak when you do. So this is an experiment where the same cantilever under the same setting can be driven either dither-piezo or using magnet. So the same cantilever, we just switch the excitation, whether we do it using a piezo or do it magnetically, okay? If you do it using a magnetic excitation, you would get something like a blue curve, the green curve shown there. When you do piezo excitation, you see you get many peaks and resonances. These are called the forest of peaks. The question is, what's happening? Okay, why does it happen? It's a very well-known thing, and what influence does it have on AFM imaging? Okay, so before we go to talking about what influence it has, let's try to understand what is the cause of this, okay? So I'm basically trying to summarize in a nutshell where it comes from, okay? So, remember, what is happening here is you've got somewhere embedded behind your holder, you've got a piezo, right? You apply an oscillating voltage, so the piezo starts to vibrate. As it vibrates, it moves, it starts shaking whatever it's attached to, right? Whatever it's attached to is going to be attached to the chip holder. So the chip holder starts shaking. The piezo itself has its resonances. You know, there are certain frequencies at which the piezo will shake more, certain frequencies at which it doesn't shake much, right? So the piezo has its own resonances. The chip holder has its own resonance. There are some vibration frequencies at which the chip holder is going to vibrate more, and at some places it doesn't vibrate more. The chip itself has its resonances, so there are some frequencies at which the chip vibrates more and where it doesn't. So interestingly, what I want you to focus on is what is going to be, because as far as we're monitoring the cantilever motion, right, with the photodiode. So really, our interest is, you know, we may not be interested in all these paths of vibration, but what we want to know is how much does the base of the cantilever move up and down by. This is something important for us, right? So at the end of the day, if you look at that, the shaking of the base of the cantilever as shown by the red arrow, it's some sinusoidal forcing, y0 sine omega t. The key point is that the amount by which you shake it up and down depends on the frequency. So if I plot y0, which is the amplitude of shaking of the base of the cantilever as a function of frequency, if you make this measurement, and we've made this measurement, you'll find many peaks there. Okay? What are those peaks? Those peaks has simply to do with the fact that, look, as I mentioned to you, as you sweep the frequency, you might hit a resonance of the piezo, in which case the piezo vibrates more, and the base of the cantilever vibrates more, right? So maybe the first peak here might have been a resonance of the piezo, right? Piezo resonates and, you know, shakes the base of the cantilever more, but as you increase the frequency a little beyond, you're off resonance, it doesn't vibrate as much anymore. Then you come to another peak that has to now do with the chip holder is resonating, causing the base of the cantilever again to increase in vibration, reaching a peak here, and then that dies out as you drive frequency above that, and so on. So really, if you look at the base of the cantilever, you have all these resonance peaks that are there. They're there in air also, right? The key thing is, it turns out all these resonances have Q factors that are around 10, roughly order of magnitude 10. So when you put it in air, what ends up happening is Qs of cantilevers are about 100, right? Most cantilevers are 100, 150, 200. So in air, this forest of peaks doesn't play a very big role because the cantilever has the highest Q of all these resonances. So these resonances are roughly a Q of about 10, right? But the cantilever's resonance is 100, maybe 200. So it stands out like Sears towers. You know, so you might have Sears tower on a rough sort of terrain, but the Q, which makes the height of the peak and the slimness of the peak, you know, it affects that. It stands out. So in other words, if you do this in air, the Q of the cantilever itself is going to make the resonance of the cantilever very narrow, make its height very high, and so you get, when you observe the tuning curve, you get a clean response, relatively clean, okay? Because it's much sharper compared to all these other fluctuations that lie underneath it, okay? So if you zoomed in on the side in air, you will see some of these fluctuations, right? But in air, the Q of the cantilever is so much higher than all these other Qs of these resonances that you don't really see the rest. And what you see is a nice clean Q of the cantilever. In liquid, Q of the cantilever falls below 5, typically 1 or 2. So the Qs of all these resonances are now greater than the Qs of the cantilever. And you can sort of see that here. So if you see here, you see that, you know, the green is telling you something about the natural Q of the cantilever, right? Because it's magnetic excitation or thermal excitation, and you see a nice rounded response curve. But when you shake it, you get these sharp peaks shown in red, right? These sharp peaks are therefore not the resonances of the cantilever, but you're picking up the resonances of the other things that are underneath it. So the key point is, in water, the Q of the cantilever becomes lower than the Qs of these resonances. And what you see then are these resonances. In air, the Q of the cantilever is much larger than these resonances, so it stands out. It's the sharpest, tallest peak. But in water, the Q of the cantilever has come down a lot. And so the peaks that you start seeing are actually peaks of these other resonances because their Qs are larger. Okay? This is one of the key things that happens. So this is the main mechanism for this. And so when you choose one of these peaks, you have to keep in mind that it's the resonance, what you're capturing in that peak is not the resonance of the cantilever, it's the resonance of something else that's shaking. Okay? It may or may not be important, it depends, right? But there are a lot of applications for which this does become important, especially if you do frequency modulation, where you try to change the frequency, and so on. So there are many methods to try and reduce these forest of peaks. Not surprisingly, there are two ways generally of doing it. So remember, the peaks occur due to the piezo causing a resonance of all these other structures. Each peak is a resonance of one of these structures. So you can do two things. You can bring the piezo close to the cantilever, right? That's one option. If you bring the piezo close to the cantilever, as close as possible, you reduce the number of structures that can resonate, right? If you keep it very far away, then you shake more things in between, right? So try to get the piezo as close as possible to the cantilever. So that's what you see in the example above. In fact, Vicos has something called ActiveX technology. They realized this and they brought the piezo, basically they deposited piezo material on the cantilever itself. That's the ultimate. You've completely got rid of the middle person, directly exciting the cantilever. But after this adjustment that Aimé and Sophie Marcedone's group did, they got cleaner resonances as shown in blue. Okay? After redesigning so that the piezo came close to the cantilever. The other option is keep the piezo where it is, but all the intervening structures that are there, why not put some sticky damping material or something that damps out the vibrations of all the things in between. And so they put a clay damper to try and damp out the vibrations of all these substructures, and they've improved to some extent the resonance response, right? And of course, Fukuma's group went even deeper and did effectively they redesigned this holder based on a full finite element analysis of the acoustic impedances of these different components. And they said that it's not a question of having the right damping material. If you just get the impedances properly sorted out, then you can sort of shake only the base of the cantilever and not shake too many other things in between. So, and they also got some sort of an improvement in the forest of peaks. Okay, so you see the before, afters. This, every year someone comes up with a technique to improve this, and they have a before, after image, how they've improved the forest of peaks. Unfortunately, the problem is still there, because it might work for a certain frequency range. For another cantilever, some other peaks might come up. So, problem is not yet solved, unfortunately, and I doubt that it will. Okay, so with that, I'd like to end the lecture today, and we'll continue with AFM and liquids regarding cantilever dynamics in the next class, and so I'll see you then. Okay, thank you. Any questions? Yeah.
Why wouldn't they just go with magnetic excitation? What's the limitation?
Oh yeah, magnetic. Yeah, good question. So what are the choices? Magnetic excitation has problems in the sense that you have to use a chromium-based coating, and they oxidize easily. So you buy one of these magnetic cantilevers, and they don't stay very long. So then people say, why not put some magnetostrictive materials that gives you a wider range of materials that don't oxidize very easily. Again, trying to deposit magnetostrictive materials and make sure you don't get much strain, residual strain to curve it up. The process things are not sorted out very well. If you look at the Lorentz force actuation, we talked about these direct mechanisms before. So for example, There's another mechanism, which is the Lorentz force mechanism, where, let's say you've got a triangular cantilever, you pass an alternating current through that and have a permanent magnet sitting under it. You get Lorentz forces. Exciting. That's also good, but there you're supplying some current, and there are problems with supplying current in electrolytic solutions. As long as you don't apply too much current, you don't get electrochemistry, but you have to do it so that the currents you supply are small enough. But if you're trying to drive with large amplitudes, the Lorentz force actuation is not good because you're applying large voltages and you can get electrochemistry. The third approach is to use photothermal excitation. That's very popular these days, especially the frequency modulation people are really doing this, where they use a blue laser to periodically heat a cantilever directly and make it oscillate. It makes your AFM look very cool because there's a blue glow about your AFM. But on the other hand, you also have to be concerned about the cantilever might be heating up itself under this laser. So no clear method has come up yet. Each one has challenges, but it's good to know the differences and the advantages, disadvantages, so you can choose the right tool for the right task. So, good question. Thank you.